In this video, we are going to discuss this question. We know that this equation is not separable. This is a differential equation, a first order differential equation, and we know that it is not separable. But why? How can you explain why this is not separable? Well, many of you probably are going to say, well, of course, it's the sum of two expressions, one depending on x, the other one depending on y. It cannot be separable. It cannot be separable. But okay, let's continue asking the question, why? And then in the first place, we are going to introduce a definition of separable differential equation in a formal way. First order differential equation is called separable when it can be expressed in this way. In the left side, we have the derivative of y with respect to x. In the right side, we have a multiplication of two expressions where the first factor here depends on x and the second factor depends only on y. Now, why they are so important? Why separable differential equations are so important? Because we can separate the variables. It means you can, if you are trying to solve an equation like this, you can move the g sub 2 of y that appears here in the right side to the left side dividing and the dx multiplying to the other side, so you get an expression like this. And now you can integrate both sides, and by integrating, you can find the solutions of this given equation. At least most solutions of that equation can be found in that way. And now, but let's back to our question then. Our question was, well, that this equation is separable, but we want to answer why. And then let's compare our equation with the general form of a separable equation. And then you see that for our equation to be separable, the x plus y must be representable by an expression like this. And is this impossible? And we can generalize our question here. We can also think of a more general question where in the left side we have a function f1 that depends on x plus a function that depends on y, and we want to see whether it can be expressed like the product of these two factors, where the first factor is a function depending on x, the second factor is a function that depends on y. Of course, many of you are going to say, of course, this is impossible. But you know what? This is not always impossible. For example, it is not impossible when one of the functions in the left side here, f1 or f2, is a constant. If at least one of these two functions is a constant, then this is possible just by taking one of these two functions like identically equal to 1 and the other function depending on the variable that appears in the left side. It means if you make the f of 1 of x equal to a constant, then the whole left side can be considered like a function that depends only on y. And then by taking g sub 1 of x identically equal to 1 and g sub 2 of y identically equal to the expression in the left side, that's it. In this case, this is possible. But a part of this case, besides this case where at least one of the functions in the left side is a constant, do we have any other possibility where this is true, where we can have an equation like this? Well, this is what we want to answer now. And of course, this is not so obvious. Many of you might think that this is very obvious, that it is impossible, but this is not so obvious. For example, not always when you have something very obvious, like for example here, you have an expression that depends on x plus y. You might think that this cannot be expressed as the product of f of x times f of y, but this is true. This is not the same question that we are trying to discuss, but because in this case you have a function f evaluated at x plus y, but here we don't see any products. Even when we don't see any products in the left side, it can be considered like equal to a product, especially in this case when f of x is equal to e to the x. And therefore, it means that our question is the answer to our question before is not so obvious. So this question, the answer that this is impossible and is possible only when at least one of the functions in the left side or both functions are constant, is not so obvious. Nevertheless, we can state the following proposition that shows the beauty and the power of mathematics to answer questions that can be very, very general, but in a very precise way. In this case, the proposition says that for whatever four real value functions f1, f2, g1, g2, if f1 and f2 are not constants, then the equality or the equation f sub 1 of x plus f sub 2 of y is equal to g sub 1 of x times g sub 2 of y cannot be true for all values of x in the domain of f1 and all values of y in the domain of f2. Now, we are going to see the proof for this proposition, and to prove it, we are going to use the contrapositive. So instead of proving this proposition, we are going to prove the contrapositive that you know that the contrapositive of an implication and the actual implication are always equivalent. That's why we can always reduce the problem of proving an implication to proving the contrapositive of that implication. Let me write down the proposition again, but in the form of an implication. So here you have that if f1 and f2 are not constant, then this equation is not possible. And then what is going to be the contrapositive of this one? Well, the negation of the second of the consequent here must imply the negation of the antecedent. It means that the contrapositive can be expressed in this way. If this equation is possible, then either f1 or f2 is constant. And this is what we are going to prove now. And then here, of course, the equation that we are trying to that we are discussing here is a functional equation. So we are going to use methods of functional equation to prove that implication that we have before. And now let's assume that x1 is in the domain of f1, and let's assume that y1 belongs to the domain of f2. And then to simplify the notation, we're going to assume that we're going to use a, the letter a, to represent f sub 1 of x1, the letter b to represent f2 of y1, the letter c to represent g sub 1 of x sub 1, and the letter d to represent g sub 2 of y sub 1. Now, due to the original equation, if in this is the original equation here, in this equation you replace the x by x1 and you replace the y by y1, we obtain this equation for the numbers a, b, c, and d. It means that a plus b minus cd is always equal to 0. Now, let's start again from our original equation. The original equation is this one. And then now we're going to replace the y by y1. When we replace the y by y1, we obtain this. We obtain that f sub 1 of x plus b is equal to d times g sub 1 of x. And now let's replace the x by x1 in that original equation again, the one that we have on here on, you know, at the beginning of this screen. And then here we're going to, or this slide, and then we are going to get that a plus f sub 2 of y is equal to c times g sub 2 of y. Remember that the b represents f sub 2 of y1, the d represents g sub 1 of x1, g sub 2 of y1, then a represents f sub 1 evaluated at x1, and c represents g sub 1 evaluated at x1. And then we have these two equations. And now here we can divide our proof into two cases. The first case is when either the d, this number that appear here, or the c is equal to 0. Whenever c or d is equal to 0, then you can see from the last two equations here that either f1 or f2 would be constant. Yeah, why? Because, for example, if the d is 0, you can see that f1 of x plus b is 0, and therefore f1 of x is equal to negative b, so it's a constant. And the same thing happens when the c is 0. If the c is 0, then f sub 2 of y is going to be plus a is going to be equal to 0, so f sub 2 of y is going to be equal to negative a, so it's going to be a constant. Now, what is the other case? The other case is when both are different from 0. It means when c is different from 0 and d is different from 0. And now we're going we need to prove now again that f1 or f2 must be a constant in this case. So again, we're going to start with our original equation, which is this one, the one that we are assuming that is true. We are going to multiply both sides by the number CD, C times D, and therefore we get the following. We get CD times f sub 1 of x plus CD times f sub 2 of y. And in the right side, we multiply also the product of g sub 1 times g sub 1 of x times g sub 2 of y by CD. But we're going to put the factor d together with g sub 1 and the factor c together with the g sub 2. Now, you can see that the dg sub 1 of x can be replaced by this expression, f sub 1 of x plus b, and that c g sub 2 of y can be replaced by a plus f sub 2 of y. And therefore, we obtain this equation here. And now, doing the multiplication in the right side, and moving all the terms to one of the sides, and combining some terms, we get the following equation. We get that f sub 1 of x times f sub 2 of y times plus this number a minus cd times f sub 1 of x plus this number b minus cd times f sub 2 of y plus ab is equal to 0 for whatever values of x and y, of course. And then remember that we have seen that a plus b minus cd is equal to 0. Therefore, the number a minus cd, that is the one that appears here, is minus b is equal to minus b, and the number b minus cd, which is the one that appears here, can be replaced by minus a. And therefore, by making this substitution into the previous equation, we obtain this simplified equation, which is incredibly simple. And then now we can factor the expression in the left side of the equation in this way. So it is going to be f sub 1 of x minus a times f sub 2 of y minus b in the left side and 0 in the right side. Now, from this equation that should be true for any values of x and any values of y, we can conclude that at least one of the two functions has to be constant. Why? Because, for example, if f sub 1 of x is not constant, then there should be a value of x where f sub 1 of x is different from the a, so this factor is going to be different from 0. And then the second factor is going to be 0 for all values of y. All values of y. And therefore, f sub 2 would be constant in that case. Now, if f sub 2 of y was not a constant function, and then there should be a value of y where f sub 2y minus b is different from 0, and therefore f sub 1 of x minus a is going to be always equal to 0 for all values of x, and therefore f sub 1 of x is going to be constant in that case. So it means that this equation implies that either f sub 1 or f sub 2 is a constant function on the respective domain, that at least one of them is a constant on their domain, on its domain. So it means that we have proved the proposition by proving the contrapositive of that proposition. So it means that whenever f1 and f2 are two non-constant functions, we cannot have an equation like the one that we have before, the equation that says that the sum of f sub 1 of x and f sub 2 of y can be expressed as the multiplication of two functions, one depending only on x and the other one depending only on y. And therefore, we can conclude that this cannot be separable. We can rest assured that this is not separable, separable because you cannot express the x plus y as a product of that type, a product of g1 of x, or the form g1 of x times g2 of y. The same thing happened with this example. The same thing happened with this example. Well, this is it for this time. This is the end of the video. I hope that you enjoy what we the topics that we were talking about here, and that you enjoy the video, and I invite you to watch my next video. Thank you, and see you soon in my next video.